Welcome, everyone. Today we'll explore how water ingress drives key failure mechanisms in reinforced concrete and why proactive waterproofing is essential. When water sneaks into concrete, it sets off a chain reaction of deterioration. Steel bars rust, concrete cracks, and surfaces stain or grow mold. We'll cover the most common failure modes: carbonation, chloride-induced corrosion, efflorescence with mold, and freeze-thaw damage, all aggravated by moisture. These aren't just technical issues, they impact your projects. As owners, designers, distributors, and applicators in construction chemicals industry, understanding these processes helps you extend structures' life and avoid expensive repairs. Industry experts note that most early failures of concrete structures start with water and salt reaching the rebar, leading to a death spiral of corrosion, cracking, and spalling. The good news, with the right waterproofing strategies, we can break that cycle. Let's dive in. Our first failure mechanism is carbonation, essentially carbon dioxide attacking concrete. Here's how it works. CO2 from the air enters the concrete and dissolves in pore water, forming carbonic acid. This acid reacts with calcium hydroxide in cement, producing calcium carbonate and dropping the concrete's pH from a highly alkaline 13 to around 9. Normally, steel rebar is protected by high alkalinity, forming a passive oxide film on the steel. But once the pH falls, that protective film breaks down and the steel starts to rust. Rust, iron oxide, occupies up to 6 times the volume of the original steel, so as it forms, it pushes against the concrete, causing cracking and surface spalling. You've probably seen concrete where chunks have popped off, exposing rusted rebar. That's likely carbonation at work. It begins as soon as concrete is exposed to air and typically advances 1 to 5 millimeters per year, depending on how porous the concrete is. Notably, moisture accelerates carbonation. Water in the pores is needed for CO2 to form carbonic acid and diffuse steeper. Dry concrete carbonates slowly, but in damp conditions the process speeds up. In fact, carbonation is considered the most common cause of reinforcement corrosion in above-ground structures. The damage from carbonation is serious, but it can be prevented or slowed by keeping CO2 and water out. For example, using anti-carbonation coatings that act as a waterproof, CO2-resistant barrier. The takeaway: carbonation is CO2 plus water equals corrosion, and without moisture, this reaction largely stalls. So controlling water ingress is key to mitigating carbonation damage. Next up is chloride ingress, often called salt attack on reinforced concrete. The culprits are chloride ions, mainly from seawater or de-icing salts, and they are extremely aggressive to steel reinforcement. These ions sneak into concrete through the same pathways as water: open pores, cracks, any path moisture can travel. Once chlorides reach the steel, they chemically disrupt the passive oxide layer even if the concrete is still alkaline. Research and standards show that at around 0.2 to 0.4% chloride content by weight of cement, the protective layer on steel is destroyed. What follows is pitting corrosion, very localized, pinpoint rusting of the rebar that can eat holes into the steel. Unlike uniform corrosion, pitting from chlorides is insidious. The steel can look fine on the outside, but have deep pits weakening its cross-section. Chlorides also turbocharge the corrosion reaction, leading to much faster rust formation. Even in a high pH environment, chlorides can trigger corrosion at specific spots. This is why a salt-exposed structure, like a bridge by the coast or a parking garage with winter salt, might see rebar failure much sooner than expected. The physical damage is similar to carbonation: rust expands, concrete cracks and spalls. But chlorides often cause earlier and more severe failures. Think of chunks of a seaside pier or a marine pillar falling off due to rusted rebar within. Critically, it's water that carries these salt ions in. Dry salt alone on concrete surface is not a problem. It's when water dissolves the salt and the solution penetrates that chlorides reach the steel. So preventing water ingress also means preventing chlorides from getting in. Waterproofing coatings, sealers, or admixtures can greatly reduce chloride penetration. Not all concrete problems are as structurally dire as corrosion, but they can be telltale signs of water intrusion. Two such indicators are efflorescence and mold. Efflorescence is that powdery white deposit you often see on basement walls or exterior concrete/masonry. What is it? It's basically mineral salts that water carried out of the concrete. Here's the process. Water infiltrates the concrete, dissolves soluble compounds, like calcium hydroxide from cement or salts from aggregates or mortar. When that water reaches the surface and evaporates, it leaves the salts behind as crystals. The result is a white, sometimes fluffy-looking residue on the surface. Efflorescence itself is not structurally harmful. It's mostly an eyesore. You can often scrub it off or wash it with mild acid. However, it's a big warning sign. In other words, if you see efflorescence, water is going where it shouldn't, and that means other problems, like corrosion or concrete softening from leaching, could follow. Now, mold and mildew. These grow on damp surfaces, often accompanying efflorescence in wet basements or water-damaged walls. Concrete itself isn't organic, but mold can grow on paint, dust, or other materials on a damp concrete surface. High humidity and persistent leaks create an ideal environment for mold. You might notice black or green patches, a musty smell, etc. Mold doesn't directly weaken concrete like corrosion does, but it damages finishes, air quality, and can even interfere with concrete's pH at the surface. Plus, for building owners, mold is a serious liability due to health risks. The key is that both efflorescence and mold are symptoms of water ingress. They tell us that waterproofing has been compromised somewhere, maybe a failed coating, a crack in the wall, poor drainage, etc. As professionals, when we see these, we should not just clean them and move on. We must address the root cause, moisture. By fixing leaks, improving drainage, and applying proper waterproofing measures, we can stop the water movement that causes efflorescence and deny mold the dampness it needs. In tropical climates especially, I'm sure many of you have seen how constant humidity plus a bit of leakage equals mold growth in no time. That's why a solid waterproofing strategy is also about maintaining a healthy environment and good appearance, in addition to protecting the structure. Our next mechanism is more relevant to cold climates, freeze-thaw cycle damage. Even though many of us work in warmer regions, it's worth understanding, especially for high-altitude projects or materials export, and because climate patterns can surprise us. Concrete's pore network will absorb water like a sponge. When temperatures drop below freezing, that water turns to ice and expands about 9% in volume. If the pores are saturated, there's no room for expansion, so the ice pushes against the pore walls, generating stress. The concrete can't relieve that pressure, so it cracks internally. On a microscopic level, you get tiny cracks. On a macro level, you'll see the surface start to scale or flake off. Engineers often say the concrete surface is popping off, literally pieces can break away. Imagine a driveway or a parking deck after harsh winters. It looks pitted and rough. That's freeze-thaw spalling. Now, de-icing salts make freeze-thaw damage worse too. Salts can draw more water into concrete and also reduce the freezing temperature, causing more freeze-thaw cycles within the concrete. The result can be severe surface damage in just a few winters. The classic prevention here is air-entrained concrete. Tiny air bubbles intentionally added to the mix provide space for ice to expand without cracking the concrete. But for existing concrete, keeping water up via sealers or waterproofing treatments is a key defense. In tropical or subtropical zones, you might think we're off the hook with freeze-thaw, and largely that's true. You won't get freezing in lowland tropical climates. However, in some regions, elevated areas or unexpected cold spells can introduce freeze-thaw risks. And as climate change causes more erratic weather, some places are seeing unusual frost or more dramatic temperature swings. Industry voices note that climates, which traditionally stayed below freezing all winter, are now hovering around 0 degrees Celsius at times, causing more frequent freezing and thawing cycles, which are extremely damaging to concrete. So if you're working on a project that might ever face freezing temperatures while wet, for example, high-altitude construction in a subtropical region or infrastructure in temperate zones, waterproofing to minimize water uptake is critical. The less water inside the concrete, the less damage when it freezes. In short, freeze-thaw is the poster child for physical water damage in concrete. It's a purely physical mechanism, water expanding, that can be effectively mitigated by keeping water out or providing relief space inside. By now you've noticed a common thread. Water is the enabler for almost every concrete failure mechanism we've discussed. Let's reinforce that point. Moisture is the catalyst and vehicle for chemical attacks. Take carbonation. If concrete stayed completely dry, CO2 diffusion alone would have a limited effect. It's when CO2 dissolves in pore water to form carbonic acid that it can neutralize alkalinity and penetrate deeper. Similarly, chloride ions typically hitch a ride into concrete dissolved in water. Pure dry salt crystals on a surface won't reach the rebar. It's salt in solution that migrates through the capillaries. Critically, corrosion of steel needs water. Dry steel in dry concrete won't rust because there's no electrolyte. But moist concrete creates a conductive path for ions, allowing tiny galvanic cells to form on the steel surface. That's why corrosion rates jump when concrete is wet. If you've ever seen a corrosion rate versus humidity graph for rebar, it's basically flat in very dry conditions, then shoots up once the concrete's internal humidity passes about 60 to 70%. In practice, a structure that's always dry inside can remain intact for centuries, whereas one that's frequently wet can deteriorate in decades or less. Moisture literally connects the dots for aggressive agents to reach the steel and for the electrochemical rusting process to proceed. Moisture also causes material leaching. We touched on efflorescence. That's water dissolving calcium hydroxide and other salts and carrying them out to the surface. Internally, that leaching can increase porosity and reduce concrete strength over time. You might have seen old concrete that's been in flowing water. It can become chalky or develop hollow spots because water slowly washed out the lime. That's essentially internal erosion by water. Physically, we saw how water causes freeze-thaw damage by expanding. Even without freezing, long-term water saturation can soften concrete a bit. Water also contributes to alkali-silica reaction and sulfate attack. The bottom line, if you could magically keep a reinforced concrete structure 100% dry internally, you'd eliminate about 90% of the mechanisms that cause deterioration. Realistically, that's hard to do, but it underscores that controlling moisture is the #1 key to durability. This is exactly why standards emphasize Principle 1, protection against ingress. It's better to stop water from entering than to deal with the damage later. So when we talk about waterproofing, it's not just keeping basements from leaking. It's preserving the very chemistry and integrity of the concrete by denying water the chance to act as a catalyst of decay.